Okay, guys, so we're gonna talk. Hold on. Okay, we're gonna talk about sound. So if you should have done the first two practices, and then there is a lab that's a virtual lab. If you have any troubles whatsoever with that, please make sure that you let me know. Okay, so sound. Sound is a form of energy that travels in waves. Okay, so it travels just sort of the same way the ocean does, if you've ever been to the ocean. Okay, the energy, hold on. Okay. Okay, so you want to go right there? And, okay, I don't know. That's quite interesting. Let's try that again. Okay, so very interesting. Oh, I'm sorry. I'm sorry. Let's try one more time. Do you have me for any other classes? I don't think so. I don't know why it's not doing that. Okay, so what does this go to advanced? There you go. Okay. All right. Hi, Jamie. Okay, so
That's not me.
I know. Okay. You look very nice.
Thank
Got a job? Oh, but you look nice. Okay. Pardon me? Nice. Okay, so sound is a form of energy. It's produced by and transmitted by vibrating matter. It travels in waves. It travels more quickly through solids than liquids and gases. You are not. Did I not allow you in?
No, I said it's
I don't even see you. Try again. Okay, so sound is carried to our ears through vibrating air molecules. And even though, like the webinar, not the webinar, I'm sorry, but the video is more about the sound and the tones and the pitches, we're going to get into this. But this is actually how you actually hear. It's carried to our ears through the vibrating air molecules, and our ears take in sound waves and turn them into signals that go to our brains. All right, so sound waves move through three parts of the ear: outer ear, middle ear, and inner ear. So I don't know if you guys have ever had an earache, but when you have an earache, you really can't hear very well because everything is all plugged up. It doesn't go through the inner ear as quickly, or I guess maybe too quickly because it's all filled with gunk. That's enough of that. Okay, vibration. Vibration is just a back and forth movement of molecules of matter. So, and when you listen to the video, the string of the guitar is vibrating back and forth. And so it's kind of like a tuning fork, and this is pure sound. And you see how the waves are there's no other kind of interference with it. And then when you have noise, or if you think about it, the same thing pounding a hammer is, you're still going to get these waves. It's just that there's a little bit of interference in there. Okay, where molecules are being pressed together as the sound wave moves through matter. So this is compression. And for example, a wave travels through the springs just like sound waves travel through the air. So if you kind of think of this as a slinky, when you start out, it's all compressed close together, and then you spread it, and as you spread it, it sort of moves across the floor. And as it moves, there's just compression places throughout the slinky, right? So the places where the springs are close together are called compressions. Alternating areas of high and low pressure in the air, these are sound waves. All sound is carried through matter as sound waves, and the sound waves move out in all directions from a vibrating object. So again, the strings of a guitar are vibrating, and that's how we hear the different sounds. And if you place your fingers in different places along the neck of the guitar, you hear different pitches, right? Because it's either a really high pitch or a really low pitch, depending on where you place your fingers. So each wave has a unique pattern, a frequency, a wavelength, and an amplitude. A tuning fork, this is pretty pure sound. A flute, it has a little bit more, there are different kinds of interferences. I don't know. I could not read that one. Again, but these are sound waves as they're going back and forth. And then a gong is one of those big, I don't know, bell sort of things. And these are the wavelengths, or the way that you hear things through a gong. Okay. So the medium, and and if you hear anything, then that means that the waves are traveling through a medium. If you don't hear anything, that means that you are in a vacuum, because sound does not travel in a vacuum. All right, so it's a material that sound, a form of energy, needs to transfer. Speed of sound, if it's solid, it's going very, very fast. If it's liquid, it's medium. Gas, it's slow. And in a vacuum, there is no sound. Like space, exactly. That's like a vacuum. So wavelength is the distance between one part of the wave and the same part of the next wave. So this is a wavelength, where it starts and where it ends. So travels like that, right? Starts here, goes up, goes down, ends back here. You could also go from crest to crest. You could go from trough to trough. Make sense? Frequency is the number of waves moving past a point in 1 second. So if you look down here, this is a really high frequency because it's traveling very fast. And as it travels slower, or there's less waves past a point in a second, that's a lower frequency. Pitch. Pitch is a measure of how high or how low a sound is, and it depends on the frequency. So if you have a low pitch, you're going to have a low frequency or longer wavelengths. So if you think about it, and if you think about it in relationship to a guitar or a violin, if you do not put your fingers on the frets at all, you're going to have a low pitch. And the closer you get to the other end, you know how they're tied at both ends, right? So the closer you get to one end, or the shorter you make the string, the higher the pitch, the higher the frequency, the shorter the wavelength, because it's going to rotate, or not rotate, but vibrate faster. Does that make sense? Okay, so pitch depends on frequency, and here's some examples. Instruments can be played at different pitches by changing the lengths. So another way to make a different pitch is to change the thickness of the material that vibrates. So a trombone mutes, that's this thing right here. Have you seen those things in instruments? Okay. If you ever listen to jazz or watch any kind of jazz concerts, they have these kinds of things, and it mutes the sound. So it absorbs some of the sound waves that are produced by playing a softer note. So it makes a softer note. Does that make sense? When you mute something, it makes it softer. Okay, ultrasound. These are sound waves moving with frequency above the normal human hearing range. So the sounds in the range of 200 to 400 kHz. K is Infrasound? Sounds with frequencies below the normal. So if you think about it, these are sounds when you like blow a dog whistle, although I've never heard a dog whistle.
If you blow it, if you do it at a high enough frequency, you'll hear it.
Okay.
No, actually, it depends on like their age.
That
Cause
could
like
be.
I know like little kids, like you could blow like at a medium frequency, but you also start like
They can hear it.
ringing, yeah.
So it does. I guess it would depend on your age.
Because I did it to my grandma, she didn't hear anything. It was at a high frequency.
Yeah, I probably couldn't hear it either. So an ultrasound, and mostly what we think of when we think of ultrasounds, or what I think of. Okay, that's pretty interesting. Sorry about that. I guess maybe I just did it. When I, it keeps doing that. Sorry, I'll fix it. Okay, so when I think of an ultrasound, I think of seeing a baby, right? When they take those pictures, when they try to determine. What's the matter?
He wants you to slow down. He's trying to say notes, but you skipped it.
Oh, sorry. Thank you. I'm not looking there. I should look. James, do you want me to go back? Sorry, I didn't see that. Okay. And just so you know, James, this is being recorded, so you can always go back and listen to the recording. Okay? Let me know when you're ready. No, that's okay. Let me know when you're ready. And actually, Tay, that's pretty interesting. I guess I never thought about that, that when you blow a dog whistle, the younger you are, the more you can hear it. Do you, have you ever thought of that? I never thought of that. I wouldn't be able to hear it. I can't hear it when people talk to me. But that could be that I just don't want to hear it. Okay. So again, this is a picture of an ultrasound, and when you think of it, you usually think of little taking pictures of babies or ultrasounds. I guess you can also take pictures of like your bones. That's kind of what an X-ray is. Okay, so the amplitude of sound. You can control the volume, the loudness, the strength of the wave, and that's measured in decibels, or the energy of the wave. And here's, if you're whispering, it's very low decibels. Threshold of pain. I guess when you kind of think about it, you kind of scream a lot. But a jet engine, these are, the sounds that they make. Loudness and decibels and the hearing damage. So in the average home, you shouldn't have any hearing damage. Loud music, you know how they always tell you, and I know there's a couple students around here that listen to their music so loud that I can hear it. Okay. I'm not talking about now. But you're going to have hearing damage, whether you think so or not. You will if you listen to it, put it in your ears and you listen. Okay, a rock concert, progressive, and a jet engine, if you're around it for very long, it's pretty painful. Whoops. Okay, speed of sound. The velocity of a wave is the frequency times the wavelength. So again, remember the frequency is the number of times it passes a specific point in a second, and the wavelength is the measurement from either crest to crest, trough to trough, or if you start at one point and you go through the wave, you end up at the same point. That's the wavelength. This is lambda. Okay, so the speed of sound depends on physical properties of the medium and the temperature. Since the particles vibrate faster when they're hotter, sound can travel faster. So here's medium, and these are velocities. These are just known velocities because they've been measured. All right. Okay, so reflection, refraction of sound waves. I'm just going to go over this real quickly because it's not something that's in this week's assignments, sorry. But an echo, it's a reflection of the sound off a surface, right? You guys know that. You've been to caves or to mountain ranges where when you yell, you hear it coming back at you. Reverb, this is an electronic echo, and resonance is an electronic envelope. Spherical vessel or metal or glass with an opening and an earpiece on the opposite sides. Sonar. It's an instrument that uses reflected sound waves to find objects underwater. I don't know if any of you guys are fishermen or women, but that there is that, it's like a television, and you drop a piece of equipment into the water and it helps you find fish. And they find fish using sonar or reflective wave sounds. Okay, Doppler effect is definitely next week, so I'm going to stop here. And anybody have questions, comments, concerns so far?
I still can't get into that.
That's okay. I'll just write you down. You listened, didn't you? Okay. All right, any questions, guys? Jamie, James, Tay. No. All right, guys. Because you're here, you don't have to do the webinar and discussion part of the assignments. You just get your 4 points because I don't have to talk to myself. And everybody else has to do it. Okay. Thanks for coming. Bye. Okay.